Hey guys, we're going to be going over chapter 20, the third section, which you just did, 584 to 589. So get your stuff ready and we're going to go over this together. Make sure you're taking good notes. You're going to be doing some work with this. So a lot of terms in this section related to waves and the interactions. So a reflection, which you guys probably use in your everyday life and you've experienced, is when a ray of light, sound, or heat wave hits a surface and it doesn't go through it, so it bounces back off of it. So it's hitting a barrier and it hits back at. And then you guys are familiar with echoes. A great example of a reflected sound wave is an echo. So you guys have experienced that in areas like maybe an auditorium or a gym where it's a big, giant open area. Then we have what are called refractions. Unfortunately, reflection and refraction sound similar, so be careful when you're thinking about the difference between those two. When you're talking about a refraction, you have two substances, and then you've got a wave that bends as it goes between them or towards them. And so technically it's the bending of a wave as it passes between two substances. And of course, the speed of the wave is going to differ. So think about, for example, water and air and how the speed might change. That's what a refraction is. So it's going to change the speed of the wave depending upon the two mediums that it's in. So the most common example is when a light wave passes at an angle from air to water, and that's a great picture there that was in your book, figure 2. So the speed of the wave changes, so you can see the difference in what that light wave looks like. That's a very good example. So different colors in sunlight get refracted. You guys have seen that with the example of a prism, right? So there's different amounts of light and they get dispersed or spread out into separate colors called a prism. So I'm sure you're familiar with that. When you were younger, you probably studied those in science a little bit more. But that's a great example. Then we have what's called diffraction. And so now the wave direction gets changed because it finds an obstacle or an edge, like an opening. So think about if we were in our classroom right now, we would kind of talk about doorways and things like that. But this is the picture that your book gave. And so we can use that as our example here. So at the top, if the barrier, the opening is larger than the wavelength of the wave, there's only a small amount that gets diffracted. So you can see that in that picture, kind of in here. So the opening is large, and then here's the area. And then in the second picture here, if the barrier opening is the same size or smaller than the wavelength of the approaching wave, the amount of diffraction is larger. So you can see it kind of going out here. So that's your example there. So take a look at those and kind of study them. Then we have what's called interference. Now, we talk about interference like if you accidentally tune into two radio stations, or you can kind of hear both of them coming in at once. That's a typical example. But also like with instruments too. So we have two or more waves that result in a single wave if they combine and they overlap evenly. So we call that constructive interference. So think about troughs overlapping over troughs, or crests overlapping crests. So they line up evenly, and that would make a larger sound and actually amplify the sound, and it helps everything, right? So that's what we call constructive. If something is constructive, I always think of it as helpful, so it makes it louder and more easy to be heard, right? It amplifies it. But if it's destructive, think about that word destructive, right? So they kind of are all over the place. The crests and the troughs don't line up evenly. They're kind of off-centered. And so it kind of makes a smaller amplitude because it's all these different sounds, so to speak, or different pieces. So this was the picture your book gave, and again, if we were in class, it would be a little easier to show it, but at the top picture here, it's constructive interference. So the waves combine and overlap on the crests and troughs. So they're approaching here, and then they overlap very evenly, right? So you can see that it ends up being an amplified sound. Here, the waves are approaching this way and that way, and it's a crest and a trough, and here they don't overlap evenly, and so it ends up being kind of, like I say, a smaller amplitude and destructive, right? It's not as helpful. So think of it that way. That's a good picture to take a look at as well. Then we have what are called standing waves. So these are certain parts of a wave that sit at rest position. Other parts are at a very large amplitude. Kind of looks like it's standing still, but the waves are actually going in both directions, so it's a little bit confusing. And that's kind of a good example, if we could visualize it, of, think about a crest being super high and then part of it sitting at rest position. So we have what's called resonance, and we always mention resonance in music, right? So we have what are called resonant frequencies, right? So you have these objects that naturally vibrate, two objects, and they vibrate at the same frequency. And so one produces the sound and it causes the other to vibrate. So voice sounds louder in some areas, your voice would sound louder in some areas because of this. Instruments work this way. So here's the marimba bars, right? Some of you guys have even played these in music class. This is a great example of resonance. So it produces sound based on the resonant of the air, the resonance of the air column. So the bars are struck with the mallet, and then the vibrating bars cause the air in the columns to vibrate, and then the lengths of the columns are a different size. So if you look down here, you can see the sizes are different, really long versus way shorter here. And so they have those different lengths because the resonant frequency of the air column will match the frequency of the bar that is played. So that's pretty cool. And the air column then resonates, right, or vibrates with the bar, increasing the amplitude, so producing this beautiful loud note. So that's just one example. Other instruments might work a little bit differently, and there's other examples of resonance. Some cause things like swaying back and forth and earthquakes and stuff like that. So there's a lot of different examples there that you could research and look up a little bit more. Okay, that's this section. If you want to go back and take a look at things, you might want to take a little bit of time to do that. I went a little more quickly, and you'll be seeing this in some other work that we're going to do. So feel free to move back and take a look.